I really like.
Okay, if you guys can have your calculators out.
Maybe, bro. Yeah. I don't think I even did like. That's like we don't event.
Okay, so the thing that the calculator is going to help us out with is that the calculator is able to find derivatives at a point for us and also definite integrals for us. So for certain problems on the AP exam, you're going to be expected to need to use calculator's features for problems that are where the derivative is too difficult to do by hand or too long to do by hand. So you have two options. So either TI-84 or 3036 Pro. Either of these can help you get to these calculator features, which I will these calculus features, which I will walk through and show you. Yeah, that works. It's just the syntax is a little bit different, and so for the test, I will put the syntax on the board so that as you're getting used to the different the syntax, it's going to be a little bit cleaner on the 84 where there's math print. On the older calculators, it just looks a little bit different, but you can still get the same result. But I'll go through those steps with you. But for those of you who are using my older calculators, would you be able to eventually get your own calculator? Or okay, so it's just my older calculators, they do work. It's just it's gonna be faster if you can have your own calculator to just practice with and get comfortable with all the features. Especially as we get closer towards the AP exam. But for the time being, I think this is fine using the older ones. Okay, so there's a particle motion problem. A particle moves along the y-axis, so that means this particle is normally particle motion is moving left and right on the x-axis. Here, our particle motion problem, the object is either moving up or down. So moving up is going to indicate positive velocity. Negative velocity is now going to be down instead of left. So it says particle moves along the y-axis, given by v of t equals t sine of t squared. In what direction is the particle moving at time t equals 1.5? Well, we have the velocity function. So I think this one we can just directly plug in, right? We can just plug in 1 in for t, and whatever we get, we'll just be able to know which direction it's moving, right? If we get a positive velocity, that means it's moving up. Negative velocity, he'll be moving down. So we're just going to plug 1.5 directly into the velocity function. If you're using a TI-84, I just want to show you that, especially if you're entering the same function over and over again into the calculator, it's nice to just have it in a space where you can easily access it rather than having to type in the function every time. So here's an option that you can do. Under Y1, you can type in your expression, and also you're always using X in your calculator. Don't try to match the variable in the problem. Sometimes the problem will use like theta, or they would use t. If you try to use other variables besides X, the calculator is going to complain, or it's going to give you something that is strange. So just always use X on your calculator, but on paper, you're always going to use whatever variable that they present you. Okay, so in this case, my velocity is t sine t squared. I'm going to make it x sine x squared. Okay, so under y1, you can type in x1 x squared. And also just double check, because we're dealing with trig, we should always be in radian mode. So if you go to mode, we should always be in radian mode. I would say I think it's a good habit to just always be in radian mode, but realistically, it's only going to impact you if you're dealing with trig. If it's a non-trig problem, it doesn't matter if you're in radians or degrees, but because we're never dealing with degrees, I think it's just safer to just always be in radian mode. Okay, so y1, you have x sine x squared. If you get out of your main second mode to get down to your home screen, you can do alpha y equals. Sorry, not alpha y equals. Alpha trace. Alpha trace will give you a list of functions that you can recall quickly. And then right now, my y1 is holding my velocity function. So if I do parentheses 1.5, it'll just type in 1.5 in for all the my variables within velocity function. And in return, it'll give me my value. The other option, an older calculator, if you want to call this function, and I'll put that on the board later, is if you do vars, y vars, function y1, that's also another way to call the function that you're holding under y1. Okay, so velocity at 1.5 is 1.167. And also, if you're using a 36 Pro, then I think it's just easier to just plug in directly. I don't think it's probably not worth the trouble to try to create a function to call. So, okay, so my velocity is 1.167. That's greater than 0. So the positive velocity means, in this case, moving up. So we know that particle is moving up. Okay, part B, find the acceleration of the particle at time t equals 1.5. What's the relationship of acceleration to our given velocity function? It's a derivative, right? Now, we could do the derivative by hand. We could go through product and chain rule, but because this is a calculator section, we can use the calculator to just find the derivative. So there's a feature in your calculator under Math 8. Math 8, there's an n-deriv feature. Let me do the math print form, and then I'll put the if you're using the older calculator, the syntax for that. But either way, you're going to do Math 8 n-deriv, and this will just give you your derivative feature. You're always going to do d over dx. That's always your independent variable, so you're basically asking for the derivative of a function at a point. Okay, so we're going to put in the velocity function. It's going to build the derivative for us, and it's going to plug in the x value for us. So right now, my velocity function is held under y1. So again, if you do alpha trace y1. And so right now, this is my velocity function. I'm asking for the derivative of my velocity at t equals 1.5. And so my velocity is negative 2.049. So v of 1.5 is equal to negative a of 1.5. A of 1.5 is negative 2.049. And since my velocity is less than 0, I know that since my acceleration is less than 0, I know my velocity is decreasing. Okay, so I know there's a couple of calculators out there. So let me, this is hopefully the one that most of us have. So any questions with entry in your calculator? And so again, Math 8 will get you to that notation, and then alpha trace will get you to your y1. Now, if you want to just type in that velocity function, you're welcome to. I just, like to have that y1. It's just one button away or two buttons away to call that function rather than having to type in your entire function every time you want to use it. Okay. The other option is if you're using a 36 Pro, there's, if you see near the top of the menu here, there's that d over dx. So that's under that blue upper region there. So if you do second ln will also call a very similar notation that we just saw with TID4. But now you're gonna have to type in the function and then just always use x. So I know you have other options of other variables here, but just always use x. So in this case, we'll use x sine x squared. And I'm asking for the derivative of this velocity function at t equals 1.5. Oops, sorry. My mode should be in radian. So I'm going to go to mode, go back, get it back into radian mode. Let me try that again. Yeah, negative 2.049. Okay, if you're using one of my older calculators here, you'll still do math 8 and derivative. But it's going to actually show you this n deriv function or feature, and then it's going to come with 3 arguments. Okay. The first is you can just type in that function that we're holding, and then you're always going to use x because x is the independent variable, and then you're going to plug in whatever value here that you want to plug in. In this case, we're plugging in 1.5, so you're plugging 1.5 here. So this is the x value that you want to evaluate. And then if you want to get to that y1, can do bars, y bars, function, and then down the road, if you want multiple functions that you want to call, then you can go to y2 or y3, depending on whichever function is holding your. So it'll look something like this. If I have, let's see, I think this is an older one here. Yeah, okay. So my y1, I'm going to let it hold my velocity function. So x sine x squared. Math 8. Again, it'll come in with 3 arguments. You're going to do bars, y bars, function y1, and then you'll do comma. A comma is right above the number 7, so comma. And then you're always going to do x, since x is always going to be an independent variable. And I'm asking for the derivative of this function at x equals 1.5. That'll get you there as well. So if you're using an older calculator, again, all the calculator features, the new calculus features that you're going to see on Friday's test, I'll leave up on the board as you guys are getting used to these notations. Okay, any questions so far? Okay, part C, given that y of t is the position of the particle, find y of 2. So we have a rearranging of first theorem that's really helpful, especially with particle motion problems. And it's going to look like this. The idea is that if I'm looking for a final position, or any position that I'm looking for, it's always going to be my given or initial position plus my displacement. So what that looks like is this. If I have x of b, let's say that's my final position that I'm looking for, is equal to x of a, that's my given position, plus a to b, integral of a to b of v of t dt, that's my displacement. That's basically indicating how much distance I'm going to cover in that period. So in this case, if I want to find y of 2, adapt this formula for my problem here. If I want to find my location of the object at 2 seconds, I'm going to start off with my given position, y of 0. And I'm just going to have to figure out how much distance am I going to cover in that time period. And because we have our velocity function, if we look at the displacement under our velocity function, we can get our displacement, or area under velocity, we'll get our displacement. So integral from 0 to t of v of t dt. Now, we also have another feature in our calculator, which is finding definite integrals. Okay. So basically, for what's useful for our calculator for the AP exam is really, it just boils down to two main features, Math 8 and Math 9. Math 8 will find the derivative at a point for you. Math 9 would do a definite integral for you. So to do this feature here, again, I'll do 3 calculators. I'll do the one that most of us have. I'll do the 36 Pro, and then I'll do the older 83 with the older syntax. So this one, you're going to do Math 9, definite integral. You'll see that definite integral notation. We want to find the definite integral from 0 to 2 under our velocity function, so from 0 to 2. The velocity function we've already established under y1, but if you want to type in x sine x squared, you can. So again, alpha trace will get you that shortcut feature to call y1 dx. So now we don't have to do our full power rule process anymore, or integral process by hand. The calculator will do this for us. So we get 0.828. So that tells us that between 0 and 2 seconds, this object is going to make a forward progress of 0.828 units. Right. If you're using 36 Pro, there's the feature right below derivative. There's that integral notation there. So if you do second e, you'll get that integral notation. So you can do from 0 to 2 and type in your velocity function. So again, always use x sine x squared. We should get the same answer. 0.828. If you're using one of my older calculators there, you'll do Math 9. This is going to be your Fn integral. And that F integral will show up in your calculator. And this one will come with 4 arguments. You're still going to type in your starting function. You're still going to use x, but now you're going to do lower bound to upper bound. Okay? So in this case, my lower bound to upper bound is from 0 to 2. So in the calculator, it will look something like this. You'll do Math 9. Again, y1, so vars, y vars, y1, comma x, comma 0, comma 2. Again, I'll leave all this on the board. So right now, don't have to worry about memorizing it. Memorizing these additional features for your test.
Okay.
Yeah.
Can I put one of these already in there?
Yeah. So for that one, you'll do second e. If you do second e, you'll see that integral notation.
Oh yeah, I mean I got the answer, but it's in degree mode.
Oh yeah, so do mode, and then select radian.
Yeah, thank you.
Okay, so between these calculators, any questions? So really, when you're doing the calculator section on the AP exam, if there's something that you can use that they're going to have you using, it's usually the graphing feature, which I think many of us from AB know that. And then if you're coming from AP pre-calc, you've also done a lot of practice with graphing. And then these 2 additional features. Okay, so really calculator section is just kind of focused around these 3 features. But not every problem on the AP exam in the calculator section requires calculators. So that's also something that we have to get used to, that not every problem requires a calculator. Okay, so we get the displacement is 0.828. That just tells us how far we've gone, but it doesn't tell us where we ended up. Where we end up is going to be our starting location plus displacement. So our y of 2 is going to be starting position, starting location of 3. And then from there, we're going to move to the right 0.827. And so we're going to end up at location 3.827. Okay, it's good that we started with this problem because we can basically see all but the new features, and then they're going to get sprinkled throughout different problems as well. Next up, find total distance. So we do have a special notation for total distance, and that involves absolute value function, because total distance under, remember, when we're dealing with total distance and we're looking at the area, we always have to consider every region to be a positive region, right? And so if we want to do total distance, our formula for that is the depth integral from our starting to our ending under the absolute value of v of t dt. Okay, so let me again show you these three features in each of the calculators. So if you want to do absolute value, you're going to still do math 9. You'll do from 0 to 2. And then you're going to call the absolute value feature. So the absolute value feature is stored under math number ABS. So we get that absolute value notation to get to show up, and then you do alpha trace y1. That will basically we're calling that same velocity function again, and then dx. If you're using a 36 Pro, second integral from 0 to 2. And then the absolute feature again, same location here, math number ABS. And then type in your function x sine x squared. Takes a little bit longer for the calculator to get that. And then if you're using older calculator there, so math 9, you'll call the absolute value feature. So same location as what we saw before. So it's math number ABS, and then type in your function. So you can tell that it's not as clean as the newer math prints. So you got to do ABS y1, that basically represents that absolute value, comma x, comma 0, comma 2. Now, if we're finding total distance, we don't include our starting location. It is just the absolute value, the depth integral of the absolute value. So 1.173. So that just tells us that if we count all of the steps moving forwards and backwards in that interval, his total distance is 1.173. So in this problem, we're able to see all the new calculator features that you're going to be practicing for this calculator test. Okay. Any questions so far? Okay, next up, this is Riemann-Sum's problem here. So it says the temperature in degrees Celsius of the water in a pond in a differentiable function. So again, differentiable function, this tells us we're dealing with a smooth curve. There's no surprises in this function. There's no sudden holes, asymptotes, or sharp turns. even though we only have a couple of points across this graph, we know this graph is going to be a smooth curve in between. Okay, the table shows the water temperature as recorded every 3 days or 15-day period. So here, let me just kind of run through the table that they're giving us here. That means day 0, temperature is 20 degrees. Day 3, they measure temperature again up to 31 degrees. 6 days later, 28 degrees, 24, 22, and 21. So it looks like it rises, but then for the most part, it just decreases for the rest of the time, for the rest of the days. Okay, part A, use the data to approximate W prime of 12. So anytime you see the word approximation, that means no calculus. There's no calculus features here. We're relying on algebraic features to do approximation. So approximation of W prime of 12. We want to find the approximating the derivative at 12. We know another word for derivative is what? Slope, right? So if I want to find slope at a point, I should need 2 order pairs. So if they're giving you the exact t-value that they're asking for the slope, you have a couple of options. You can just use any points around it. You can use you can use 8 and 12, you use 12 and 15. You could also use 9 and 15. But if you're using any order pairs that's outside of these 3, then you're too far away and it's not as accurate. So any of these 3 order pairs, if you just pick 2 of them, they will be sufficient to give you an approximation that will be accepted on the AP exam. So we can say W prime of 12. I'm just going to choose to use the last 2, but you can choose the first 2 or the first and third here. So W prime of 12, change in temperature over the change in time. And then our units, it's going to change as well, right? We're doing slope. So slope is going to be change in temperature over change in days. So it's going to be degrees Celsius per day. So this tells us that on the 12th day, roughly, the temperature is decreasing by 1/3 degree Celsius per day. Okay, part B, approximate the average temperature. Approximate the average temperature. So we want to use average value theorem here. But we're still under approximation. So we're using non-calculator features here. They're asking us to do a trapezoid approximation. So I'm going to set up my average value formula first. Okay. Replace every t value with 0 and 15. Sorry, every a and b value with 0 and 15. But then for this part of it, we're going to use geometric formula. We're not going to have a formula to plug in. We're going to use trapezoids. And there's a formula for trapezoids, but I think a formula that I feel like in the past students have had trouble memorizing the trapezoid formula. So I think the easier way to do this is do a left rectangle, then do a right rectangle, and then add them up divided by 2. So if you find the average of your left and right, that's basically a trapezoid. And I think that's easier rather than having to go through it like a trapezoid area formula. So let's do a left rectangle. Left rectangle means every subinterval of 3 days. So go ahead and split up each of your subintervals. And we're just adding areas of rectangles. The nice thing is here, all the width is 3, right? 0 to 3, 3 to 6, 6 to 9, 9 to 12, 12 to 15. These all have widths of 3. Left rectangle would be width times height. The height of my first rectangle is 20. Second rectangle, height of 31. Third rectangle, and then so on and so forth. What I could also do is I can just factor 3 out. It's always the same width. So I can just factor 3 out and just add up all the heights, because rather than having to multiply 3 to every term, I can just multiply the 3 once and just add up all the heights. So 20, but I don't want to use the final heights because it's a left rectangle. So the last rectangle, I want to use a height of 22 since we're dealing with left rectangles for now. So 20 plus 31 plus 28 plus 24 plus 22. Let me multiply this and add this up. Okay, let's do right rectangles. So right rectangles means every subinterval I want to choose the height on the right. So I'll start with 31, and I'll add up all the y values all the way to the end. And then we're just going to average between the left and right, and that's going to be our trapezoid. So 375 plus 378, 376.5. Okay, so but I'm trying to find the average temperature here, so I got to still make sure I include that 1/15. So 1/15 times 376.5. Now, if we're just looking at these numbers here, we're expecting our average temperature to be somewhere between 20 and 31 degrees, right? So if you present your answer as 376, you know something is off, right? All these temperatures are between 20 and 30. Doesn't make sense that our temperature should be 376 if they're only hovering between 20 and 30. So we got to divide by 15 still. And we get 25.1. That feels a lot more reasonable. 25.1 degrees Celsius is our average approximated temperature using trapezoids. So again, trapezoids is just left rectangle plus right rectangle area, and find the average of those two divided by 2. Okay, so we have an average rate of change. We have our average, our approximated temperature, average temperature. Now C and D is going to give us a more accurate model, and we're going to rely on our calculator, our calculus features to find a better answer to A and B. So A and B, we're relying on geometric or algebraic approximations, and C and D is going to move into the calculus. So it says a student proposes a function P of T, which models the temperature of the water at any point in time. So it's going to be more accurate because it doesn't just tell us the temperature at every 3 days. It's going to be able to tell us the temperature between these days as well. Find P prime of 12. So now it's asking for, now that we have a better model, what would be the a better or a better rate of change given this model function. So P prime of 12, we can use our calculator. So P prime of 12, that's just asking for the derivative of this function. So we can work this out by hand. I mean, we can go through a product rule and chain rule, but we can use our calculator to just do our derivative. So let's do math 8, but I'm going to have my y1 hold my functions so that I don't have to type it in for part D as well. Again, you're always using x variable when you're typing in the function. So 20 plus and x e to the negative x over 3 . Again, it's showing negative x over 3, not negative 1 over 3. So now that I have stored under y1, I'm going to call math8 to have it do a derivative for us. So math8 alpha trace to call my y1 to call my p of t function. And I'm just asking for the function to give me the derivative at 12. So the better version of part A is negative 0.549 degrees Celsius per day. I mean, it is still talking about the same moment in time. It's just, this is more accurate. So temperature is still decreasing by less than 1 degree per day, but this is negative 1/3. This is a little better here, negative 0.549. Supposedly more accurate because we have a function that is accounting all the different moments in time besides just every 3 days. Okay, part D, use the function P to find the average values. So we're still going to use average value theorem, but instead of using trapezoids, we're going to type in the function and make the calculator find the area for us. So still the same formula. We're just using a different function that we can plug in the calculator. So math 9 will get you to your integral feature. I'll go from 0 to 15. I have my p of t function stored under y1 already, so alpha trace y1. Make sure you divide this by 15. You're still finding your average temperature. So 25.75 degrees, which is, it should be in line with our approximation. It's just now more accurate. Again, if you're using one of my older calculators, then you'll use that. You'll use the argument feature where you'll type in the function comma x. In this case, you'll go from 0 to 15 as your lower to upper bound. Okay, next page. So we saw particle motion. We saw a table of values, Riemann sums. And now the last type is where you're given basically a derivative function, and you're asked information about this derivative function. Okay? And the reason that this is a derivative function is because of this notation here. It tells us that g of x is the integral of f of t, and that tells us that g and f are not at the same level. I have to take the integral of f of t to make it rise up to g of x level, which means whenever you see this notation, you know that your whatever function is presented here is always the derivative function. Okay, so that just shows that g of x equals integral means that you have two functions that are staggered, and one is at a derivative level of the other. But I just want to build this relationship first before we go too far in. So I want to write these three. I want to write this function again. So g of x is basically the area under the f of t function. Okay. I want to build the relationship that we're going to need because eventually they're going to ask us about g prime, and g double prime. So that means g prime is the derivative of this, right? If g of x is the integral, then derivative is g prime is the derivative of this. So derivative means I'm essentially doing derivative of this notation, which hopefully we can recognize this as just, oh, this is basically second theorem, right? Second theorem means two opposing operations will cancel out, the other will get plugged in. So basically my g prime is my f. Again, staggered relationship, right? G and f are always going to be 1 degree off from each other. which means that G double prime would make this go down one level, means F prime. So G is the area under the F, G prime is the order pair of the F, and G double prime is the slope of F. Okay, so now that we have these three functions relationships established, we can use that to set up part B. So part B, we want to find G of 0. So to find G of 0, which is going to rely on the definition that they provide for us. So G of 0 is the area between 3 and 0 under F of t dt. Now, anytime you want to read the graph from left to right, so that below is negative and above is positive, and everything can feel a little bit more clear cut. So whenever you're trying to read the graph and the bounds are not in order, I think it benefits us to rewrite it in the order from left to right. So I'm going to rewrite this as negative integral from 0 to 3 of f of t dt. So we're basically going to be trying to figure out the area or displacement under this graph, but these are all formed by nice geometric shapes. So if we just find out each of these regions, and we can add them up and figure out what that displacement is. Okay, so let's just recall some of this is an important skill here that I think some students have trouble with, is that you see a lot of different shapes here. Maybe you see a triangle there, you see a semicircle, maybe you see multiple triangles here. You're only looking at what's between the graph and the x-axis. Yes. Oh, 0. Oh, my bad. -3. Sorry. So in that case, let's not change the bound. Thank you for showing. I misread it. Okay, so we're not going to change the bound. Sorry about that. I misread it. The formula, the definition tells us -3 to 0. So we're just going to keep it in that form. So a important step here is that we have to realize what regions we're looking at. So I think it's always a good start to just start by shading in the region that you see between the graph and the x-axis, because that's the only portion that we care about finding the area for. Any other shapes that you see is not part of our diagram. Okay, so triangle, triangle. I see a triangle above a rectangle. Here, this is basically formed by a semicircle subtracted from a rectangle, and then triangle and triangle. Okay. So some students will see a triangle here, they'll see a triangle there, but that's not part of our diagram. Okay. Just for a future reference, we're going to need all these areas down the road. So I'm going to go ahead and find each of those regions and assign the area, assign the displacement. If it's above, I'm going to make it positive. If it's below, I'm going to make it negative. So here, this is 1/2 base times height. So this is going to be a -1. Here, this is technically a trapezoid, but if we don't want to think about a trapezoid, we can always just, split up into shapes that we're more familiar with. So here I see a triangle, and I see a rectangle, and I see a triangle above a rectangle. Okay. And if we just find each of the areas of each of these regions, we can just total them together. So I have a triangle here, 1/2 base times height. I got a triangle there, 1/2 base times height, but this is going to be 1/2. Wait, sorry. 3/2. This is 1/2, 1 times 3. So this is 1.5 or 3/2. And this rectangle is just the area of 3. Here, this region here is made up of a rectangle minus a semicircle. So my rectangle is 2. My semicircle is 1/2 pi r squared. So this region is going to be 2 minus pi over 2. Here, this triangle is 1/2, and this triangle is -1/2. Okay, but right now I know we did more than we needed to, but this is what we're gonna need all this when we hit these other problems here. But the region from -3 to 0, we can just count up what we see here. So -1 plus 1 plus 4.5. So displacement is just 4.5. Next up, we want to find g prime of 0. G prime of 0. We look at the definition that we've established. G prime of 0 equals f of 0. And remember, this is the f graph. So f of 0 is just asking for the y value. So what's f of 0 equal to? Just 1. Okay, they're also asking for g double prime of -1. So g double prime of -1. We have a formula that connects g double prime with f prime. So g double prime of 1, -1, would be the same thing as f prime of -1. Now this is the f graph here. So f prime of -1 is asking for the what? Slope. Yeah. So if you look at -1 on the graph here, what is the slope of this line segment? So I just pick 2 points, right? Pick 2 points, easy identifiable points, and just do slope down 1 over 3, right? So -1/3, right? So if you're given this form, which you're going to see on the test, you're either going to be gathering the area or displacement, or you're gathering the order pair, or you're gathering the slope, depending on which level they're asking for. All right, part C, find all the values on the open interval where G attains a relative maximum. Okay, so relative maximum. Remember, this is basically acting as the derivative of G, right? G prime is the F, so this is my G prime. And so we should have to recall the fact that this is basically a derivative graph. So let's create our slope sine line. And let's remind ourselves what we're looking at. A derivative graph means above the x-axis means positive slope, and below means negative slope. On the x-axis is where your slope 0 is going to live. So I'm going to pick out my x-intercepts, which is -4, 1, and 3. And I can also put my endpoints as well, since they do establish endpoints for us. -5 to 4. And then we know below means negative slope. Above means positive slope. So negative, positive, positive, negative. Now that the sine line is in front of us, it's easy to tell that there's a relative maximum at x equals 3. Okay, part D. Find the absolute minimum value. So absolute minimum value, what does that remind you of? What theorem is that? Yeah, EBT, right? So EBT means we're going to be picking out endpoints and critical points, or endpoints and max and min. So we can pull all that data from G prime. So we're going to be testing -5, -4, 3, and 4. There's no need to test 1 because 1 is neither a max nor min. If we're not looking at a max nor min, then it has no chance of being an absolute max or min. So we basically have to use our graph to find G of -5. We'll find G of -4. Okay, I know it's only asking for absolute minimum, but I want us to just get that practice in of finding max and min in case you're finding one, or in case you're finding both. So let's just gather all the relevant points for our max and min. So -5, -4, 3, and 4. Okay, so we're relying on our definition to find our g of x. So g of -5 is simply defined as the integral from -3 to -5 under my f graph. So -3 to -5, what do you notice about the bounds here? Yeah, they're backwards, right? So let's pull a negative and make our bounds go from left to right. And that way we can just, whatever we see is whatever we get, right? Negative is below, positive is above. We don't have to switch that in our heads anymore. So -5 to -3, we know that's just going to be 0, right? That these two triangles add up to be 0. So a -0 is still going to be 0, so that's not going to change. Okay, again, we're relying on the definition that they're providing for us. The g of x defined from -3 to x, and our upper bound in this case is going to be -4 because that's the way that they've defined it. Again, my bounds end up being out of order, so I'm going to pull a negative. And then from -4 to -3, that's a +1, but I pulled a -1 already, so this is going to come down to a negative. G of 3 is the integral from -3 to 3. I'm going to add all these up here. So -3 to 3 is just going to be the rectangle, the triangle, the rectangle minus the triangle, and then adding up those two triangles. So okay, G of 4. Integral from -3 to 4 of f of t dt. Oh, sorry. There's a +1/2 in here as well. Now this is what I was talking about before. This is the rectangle, triangle, rectangle minus semicircle, and then add these two up. So this one is going to be 6.5 minus pi over 2. So then we compare between all these values. What is our absolute max? Our absolute max is going to be that 6.5 minus pi over 2. For our absolute minimum, it's going to be this -1 here. Oh, sorry, 6.5 minus pi over 2. Sorry, this would be here, this one here, 7 minus pi over 2. And then the min is -1. Okay, we'll finish up with page 2. And we'll continue working through this packet tomorrow.